We'll be doing the editorials for lead code bi-weekly contest 120. So the first question of the contest is count the number of incremovable subarrays 1. So basically in this question we are given with a integer array. Let me call it as nums. So we have some integers given here. So for now I'll be writing some random thing. So in nums we have 8, 7, 6, 6. These are the integers given. So in this nums array, we should count how many subarrays can be removed. We should count how many incremovable subarrays are there. Now let's see what a incremovable subarray means. Basically, if I remove any subarray from this, for example, let's say I remove this. Now this is removed, and the leftover part let's concatenate. So here the concatenated part is 6. So whatever leftover elements are there, which are concatenated, that forms, after concatenating those leftover elements, it forms a array. So that array should be strictly increasing. Strictly increasing. So how many such subarrays are there? Such that after removing those subarrays, after removing the subarray, which is incremovable, the leftover concatenated part of the array should be strictly increasing. So let's see some examples for this. So now if you look over subarray 8 is one of the subarray. So if I remove 8, I'm writing out removable subarrays. So these are the subarrays which we are removing. If I remove 8, then we can see this is not strictly increasing, this part. That is, after removing this, the leftover. This is the leftover, let's say 7, 6, and 6 will be leftover. So this is not strictly increasing. Now remove 8 and 7, 6, 6. This is also not strictly increasing. By strictly increasing all array elements, basically every ith element should be greater than I minus 1th element. Then we say array is strictly increasing. So here they are equal, so it's not strictly increasing. Similarly, if I remove 6, then 6. This is strictly increasing as there is only one element. Now the next subarray, if we remove, this is empty, so this is also strictly increasing. Now if we remove 7, then the leftover part is 8, 6, and 6. This is not strictly increasing. 7 and 6. This is also not strictly increasing. This is strictly increasing. Now if we remove 6, then the leftover part would be 8, 7, 6. This is not strictly increasing. Leftover part is this, and this is also not strictly increasing. If I remove 6, then the leftover part is 8, 7, 6. This is also not strictly. So among all these strictly increasing arrays are 3, these two and this one. Right? So this way we should count how many incremovable subarrays are there. Basically, this is an incremovable subarray of the given array. This is also incremovable subarray because the leftover concatenated part is becoming strictly increasing of the array. Similarly, this is an incremovable subarray. So we should count all such subarrays which are incremovable, and we should output an integer. So here, if we look at the constraints, the constraints are very less. That is, so length of the array given can be 1 to 50 only, and elements in the array can be in the range 1 to 50. So these are the constraints. Let's see how we can solve this. So from the constraints, we can see that the constraints are too small. So we can do a brute force for this. What we can do is for any subarray of the given array, we can represent it with two indices, nums of L colon R. So let's say this represents the subarray from L to R. R is inclusive. Let's consider R is inclusive. So now our aim is to fix L and R and then remove this part from the nums and then check if it's strictly increasing or not. So what we can do is we can fix L. L ranges from 1, L ranges from 0 to n minus 1 inclusive, and R ranges from L to n minus 1. So here what we can do is we can remove from nums, we can remove L to R, remove elements from L to R in nums. That means this is a subarray that we are fixing. Now after removing this subarray, if the concatenated part after removing the subarray is strictly increasing, so for that we can iterate a loop to check if it's strictly increasing the concatenated part, and the loop range would be from 0 to n minus 1, because in the worst case n can be the length of the concatenated part. So we can iterate a loop and then check if every adjacent element is strictly greater than every adjacent element is strictly greater or not. If it is greater, then the current subarray from L to R, that is an incremovable subarray. So we can check this, and if this satisfies, then we can say it's incremovable. We can add +1. We can count this subarray uh, as our answer because this is an incremovable subarray. So this way we can do a simple brute force. And the time complexity here is we are basically fixing every subarray, removing that subarray, and checking if the concatenated part can become a strictly increasing subarray or strictly increasing array or not. So the time complexity of this would be big of firstly, let's analyze it practically. We can say the outer loop runs for n times into. So the inner loop in the worst case will run till n times. So we can approximate the time complexity into. To check this, we again iterate a loop, which would be n in the worst case. So we can say the TL would be equivalent to big of n cube per test case. And if you look at the space, it depends on how we implement. We can implement this with a space of big of n and big of 1 as well. And this can further be optimized as well. Like this is the first question, whereas in the third question, we have the harder version of this question where where the constraints are tightened. So we'll see how we can optimize this problem in how we can optimize this when we reach to the third question. So currently with this constraints, a big of n cube per test case is sufficient to pass the solution, sufficient to pass the problem. And space, we can implement it in big of n or big of 1, depending. It becomes n if we create a copy to check this condition, and O1 if we don't create a copy and check the same condition. So if you don't create a copy, we can do it in O1 space. So this way we can solve the problem.